Hi, I am a tutor in Uplatz. Today we are going to discuss our automotive electrics and automotive electronics part 1. Electrical and electronic systems in the vehicle. The amount of electronics in the vehicle has risen dramatically in recent years and is set to increase yet further in the future. Technical developments in semiconductor technology support even more complex functions with increasing integration density. The functionality of the electronic system in motor vehicles has now surpassed even the capabilities of Apollo 11 space module that is orbited the moon in 1969. Overview development of electronic systems, not least in contributing to the success of the vehicle, has been the continuous string of innovations which have found their way into the vehicles. Even as far back as the 1970s, the aim was to make use of new technologies to help in the development of safe, clean, and economical cars. The pursuit of economic efficiency and cleanliness was closely linked to other customer benefits such as driving pleasure. This was characterized by the European diesel boom, upon which Bosch has had such a considerable influence. At the same time, the development of gasoline engines with gasoline direct injection, which would reduce fuel consumption by comparison with intake manifold injection, experienced further advancements. An improvement in driving safety was achieved with the electronic brake control system in 1978. The anti-lock brake system ABS was introduced and underwent continual development to such an extent that it is now fitted as standard on every vehicle in Europe. It was along this same line of development that the Electronic Stability Program (ESP), in which ABS is integrated, developed in 1995. The latest development also take comfort into account. These include the hill hold control (HHC) function, for example, which makes it easier to pull away on uphill gradients. This function is integrated in ESP. The electronics in the motor vehicle, drivetrain, digital engine management, gasoline engine, motronics, diesel engine, electronic diesel control, EDC with electronically controlled fuel injection, electronic ignition, gasoline engine, lambda control, boost pressure control, turbo jet charger, etc. The electronic transmission control, onboard diagnosis, communication, electronic voice output, voice control of functions, speech recognition, audio equipment, radio, CD, etc., video, onboard computer, car phone, navigation, new display technology, display, ADAP display, internet, and PC. Safety, anti-lock brake system ABS, traction control system TCS, electronic stability program ESP, headlamp adjustment and cleaning, electronics, wash, wipe control, individualized service, travel display, motoring system for consumables and bearing parts, triggering systems for airbags, seat belt tensioner and rollover bar, vehicle security system, tire pressure monitoring, comfort, convenience, cruise control, adaptive cruise control, ACC, heating and air conditioning, heating and air conditioning, seat adjustment with position memory, power window and sun roof drive, central locking, chassis control system, backup monitoring, parking and restaurant, Platronics, Robert Bosch GMPS, Bosch Automotive, Electric and Electronics, Bosch Professional Automotive Information. Market volumes of electrics and electronics in Europe estimates 1995 to 2010, around 35% increase. Market volume is around 52 billion. Growth in 2010 is 16 billion. 3 billion euro, 20% substitution of mechanical hydraulic components, 13 billion, 80% additional electronic components. Many kinds of new functions appear in conjunction with driver assistance systems. Their scope extends far beyond today's standard features such as park pilot or electronic navigation system. The aim is to produce a sensitive vehicle that uses sensors and electronics to detect and interrupt its surroundings. Tapping into ultrasound, radar, and video sensor technologies has led to solutions that play an important role in assisting the driver, example through improved night vision or distance control. Value creation structure for the future. The latest studies show that the production cost of an average car will increase only slightly by 2010 despite further innovations. No significant value growth for existing system is expected in the mechanics hydraulic domains despite the expected volume growth. One reason here being the electrification of functions that have conventionally been realized mechanically or hydraulically. Brake control systems are an impressive example of this change. While the conventional brake system was characterized more or less completely by mechanical components, the introduction of ABS brake control system was accompanied by a greater proportion of the electronic components in the form of sensor technology and an electronic control unit. With the more recent development of ESP, the additional functions such as HSC are almost exclusively realized by electronics. Even though significant economies of scale are seen with the established solution, the value of the electrics and electronics will increase overall by 2010. This will amount to a good third of the production cost of an average vehicle. This assumption is based not least on the fact that the majority of future functions will also be regulated by electrics and electronics. The increase in electrics and electronics is associated with the growth in software. Even today, software development costs are no longer negligible in comparison with hardware costs. Software authoring is faced with two challenges arising from the resulting increase in complexity of a vehicle's overall system, coping with the volume and the clearly structured architecture. The AUTOSAR initiative, Automotive Open Systems Architecture, in which various motor vehicle manufacturers and suppliers participate, is working towards a standardization of electronics architecture with the aim of reducing complexity through increased reusability and interchangeability of the software modules. Task of the electronic system, open loop and closed loop control. The nerve center of an electronic system is the control unit. Figure 3 shows the system blocks of Motronics engine management system. All the open loop and closed loop algorithms of the electronic system run inside the control unit. The out of the control unit is microcontroller with the program memory, flash EEPROM, in which is stored the program code for all functions that the control unit is designed to execute. The input variables for the sequence control are derived from the signals from the sensors and set point generators. They influence the calculations in the algorithm and thus the triggering signals for the actuators. These convert into mechanical variables, the electrical signals that are output by microcontroller and amplified in the output state models. This could be mechanical energy generated by a servo motor power window unit, for example, or thermal energy generated by a stealth element glow plug. Communication, many systems have a mutual influence on each other. For example, it may sometimes be necessary to not only have the electronic stability program carry out a braking intervention in the event wheel spin, but also to request that the engine management system reduce torque and thus counteract wheel spin. Similarly, the control unit for the automatic transmission outputs a request to the engine management system to reduce torque during a gear shift and thereby promote a soft gear change. To this end, the systems are networked with each other. They are able to communicate with each other on databases like CAN, LAN. In a premium class vehicle, there may be up to 80 control units performing their duties. The examples below are intended to give you an insight into the operating principle of these systems. Functions and modules of the electronic system, sensors and set point generation, accelerator, pedal position, throttle valve position, EGAS, air mass flow, battery voltage, intake air temperature, engine temperature, degree of knock, lambda oxygen sensor, crankshaft speed and TDC, camshaft position, gear, vehicle speed, CAN, fault diagnosis. Control unit consists of ADC, function processor, RAM, flash, EEPROM, monitoring module. Actuators are ignition, coils and spark plugs, electronic throttle valve positioner, fuel injector, main relay, engine speed counter, fuel pump relay, one lambda oxygen, two sensor heater, camshaft control, canister punch, variable geometry intake, manifold, secondary air valve, exhaust gas recirculation. Motronics engine management system. Motronics is the name of an engine management system that facilitates open and closed loop control of gasoline engines within a single control unit. There are Motronic variants for engines with intake manifold injection, ME Motronics, and for gasoline direct injection, DI Motronics. Another variant is the bifuel Motronic, which is also controls the engine for operation with natural gas. System discretion function. The primary task of the Motronic engagement system is to adjust the torque, decide, and input by the driver depressing the accelerator pedal to operate the engine in such a way as to comply with the requirements of even more stringent emission control legislation to ensure the lowest possible fuel consumption, but at the same time to guarantee a high level of driving comfort and driving pleasure. Components, Motronic comprises all the components which control and regulate the gasoline engine. The torque requested by the driver is adjusted by means of actuators or converters. The main individual components are the electrically actuated throttle valve air system. This regulates the air mass flow to the cylinders and thus the cylinder charge. The fuel injectors, fuel system. These meter the correct amount of fuel for this cylinder charge, the ignition coils and spark plugs, ignition system. These provide for correctly timed ignition of the air fuel mixture present in the cylinder. Depending on the vehicle, different measures may be required to fulfill the requirements demanded of the engine management system. Example in respect of emission characteristic, power output, and fuel consumption. Examples of system components able to be controlled by Motronics or variable camshaft control. It is possible to use the variability of valve timing and valve lift influence the ratio of fresh gas to the residual exhaust gas and the mixture formation, external exhaust gas recirculation, adjustment of the residual gas content by means of a precise and deliberate return of exhaust gas from the exhaust strain, adjustment by the exhaust gas recirculation one, exhaust gas turbocharging, regulated supercharging of the combustion air, that is increase in the fresh air mass in the combustion chamber to increase torque, evaporative emission control system for return of fuel vapors that escape from the fuel tank and are collected in an activated charcoal container canister. Operating variables acquisition. Motronics uses sensor to record the operating variables required for the open and closed loop control of the engine. Example, engine speed, engine temperature, battery voltage, intake air mass, intake manifold pressure, lambda value of the exhaust gas, set point generators. Example switches record the adjustments made by the driver, position of the ignition key, cruise control. Operating variables processing. From the input signals, the engine ECU detects the current operating status of the engine and uses this information in conjunction with the request from auxiliary systems and from the driver accelerated pedal sensor and operating switches to calculate the command signals for the actuators. Operating variables processing for the input signal. The engine ECU detects the current operating status of the engine and uses this information in conjunction with the request from the auxiliary systems and from the driver accelerator pedal sensor and operating switches to calculate the command signals for the actuators. The diagram shows that. Air system, a specific air fuel mixture is required to achieve the desired torque. For this effect, the throttle valve regulates the air necessary for the mixture formation by adjusting the metering orifice in the intake port for the fresh air taken in by the cylinders. This is affected by a DC motor integrated in the throttle device that is controlled by the Motronics control unit. A portion of the throttle valve is fed back to the control unit by a position sensor to make position control possible. This sensor may be in the form of a potentiometer. For example, since the throttle device is a component relevant to safety, sensor is designed with redundancy. The intake air mass, air charge is recorded by sensors. Example, hot film air mass meter, intake manifold pressure sensor. Fuel system, the control unit, item 13 calculates the fuel volume required from the intake air mass and the current operating status of the engine. Example, intake manifold pressure, engine speed, and also the time at which fuel injection should take place. In gasoline injection systems, with the intake manifold injection, the fuel is introduced into the intake duct upstream of the intake valves. To this end, the electric fuel supply pump delivers fuel primary pressure up to approximately 4 kPa to the fuel injector. Each cylinder is assigned a fuel injector that injects the fuel at intermittent intervals. The air-fuel mixture in the intake passage flows into the cylinder during the injection stroke. Correction are made to the injected fuel quantity, example by the lambda control, lambda oxygen sensor, and the canister purge evaporative emissions control system. With gasoline direct injection, fresh air flows into the cylinder. The fuel is injected directly into the combustion chamber by the high pressure fuel injector, where it forms an air fuel mixture with the intake air. This requires a higher fuel pressure, which is generated by additional high pressure pump. The pressure can be variably adjusted up to 20 megapascal in line with the operating point by an integrated fuel supply control valve. Fuel injector for intake manifold injection function. The electromagnetic solenoid controlled fuel injector sprays the fuel into the intake manifold at a primary pressure. They allow fuel to be metered in the precise quantity required by the engine. They are actuated by driver stages, which are integrated in the engine ECU, with signal calculated by the engine management system. The throttle drive with potentiometric position and feedback. The injector, fuel injector. Design and operating principles. Essentially, electromagnetic fuel injectors are comprised of the following components: valve with electrical connection and hydraulic port, a solenoid coil, moving valve needle with solenoid armature and valve seat with the injection orifice plate and valve spring. In order to ensure trouble-free operation, stainless steel is used for the parts of the fuel injector which come in contact with the fuel. The fuel injector is protected against that by a filter strainer at the fuel inlet. Connections on the fuel injector presently in use. Fuel supplied to the fuel injector is in the axial direction, that is from top to bottom, top feed. The fuel line is secured to the hydraulic port by means of a clamping fixture. Retaining clips ensure reliable fastening. The sealing O-ring on the hydraulic port seal off the fuel injector at the fuel rail. The fuel injector is electrically connected to the engine ECU. Fuel injector operation. When the solenoid coil is de-energized, the valve needle and the valve ball are pressed against the cone-shaped valve seat by the spring and the force exerted by the fuel pressure. The fuel supply system is thus sealed off from the intake manifold. When the solenoid coil is energized, this generates a magnetic field which attracts the valve needle solenoid armature. The valve ball lifts up from the valve seat and the fuel is injected. When the excitation current is switched off, the valve needle closes again due to the spring force. Fuel outlet. The fuel is atomized by means of an injection orifice plate in which there are a number of holes. These holes, injection orifices, are stamped out of the plate and ensures that the injected fuel quantity remains ideally constant. The injection orifice plate is insensitive to fuel deposits. The spray patterns of the fuel leaving the injector is produced by the number of injection orifices and their configuration. The injector is efficiently sealed at the valve seat by the cone ball sealing principle. The fuel injector is inserted into the opening provided for it in the intake manifold. The lower sealing ring provides a seal between the fuel injector and the intake manifold. Essentially, the injected fuel quantity per unit of time is determined by the primary pressure in the fuel supply system, the back pressure in the intake manifold, and the geometry of the fuel exit area. Electrical activation. An output module in the motor annex ECU actuates a fuel injector with the switching signal. The current in the solenoid coil rises and causes the valve needle to lift. The maximum valve lift is achieved after the time TPK pickup time has elapsed. Fuel is sprayed as soon as the valve lifts off its seat. The total quantity of fuel injected during an injection pulse is shown in figure 4D. Current flow ceases when the activation is switched off. Most inertia causes the valve to close, but only slowly. The valve is fully closed again after the time TDR dropout time has elapsed. When the valve is fully open, the injected fuel quantity is proportional to the time. The nonlinearity during the valve pickup and dropout phases must be compensated for throughout the period that the injector is activated. Injection duration. The speed at which the valve needle lifts off HC is also dependent on the battery voltage. Battery voltage dependent injection duration extension corrects these influences. Here is EV for activation signal, current curve, wall left, and injector fuel quantity are shown in figure. Voltage dependent injection duration, battery voltage versus injection duration correction. High pressure fuel injector for gasoline indirect injection function. It is the function of the high pressure fuel injector STEV on the one hand to meter the fuel, and on the other hand by means of its atomization to achieve controlled mixing of fuel and air in a specific area of the combustion chamber. Depending on the desired operating status, the fuel is either concentrated in the vicinity of the spark plug, stratified charge, or even distributed throughout the combustion chamber homogeneous distribution. Design and operating principle. The high pressure fuel injector comprises the following components: inlet with filter, electrical connections, spring, coil, valve sleeve, nozzle needle with solenoid armature, and valve seat. A magnetic field is generated when current passes through the coil. This lifts the valve needle of the valve seat against the force of the spring and opens the injector outlet ports. The primary pressure now forces the fuel into the combustion chamber. The injected fuel quantity is essentially dependent on the opening duration of the fuel injector and the fuel pressure. When the energizing current is switched off, the valve needle is pressed by the spring force back down against this valve seat and interrupts the flow of fuel. Excellent fuel atomization is achieved thanks to the suitable nozzle geometry at the injector tip. Requirements compared with the manifold injection, gasoline direct injection differs mainly in its higher fuel pressure and the far shorter time which is available for directly injecting the fuel into the combustion chamber. Design of STEV, yes, high pressure fuel injector is shown here. One is fuel inlet with filter, electrical connection, spring, coil, valve sleeve, nozzle needle with solenoid armature, valve seat, and injector outlet. Figure shown analyze the technical demands made on the fuel injector. In the case of manifold injection, 2 revolutions of the crankshaft are available for injecting the fuel into the intake manifold. This corresponds to an injection duration of 20 milliseconds at an engine speed of 6,000 RPM. In the case of gasoline direct injection, however, considerably less time is available. In homogeneous operation, the fuel must be injected during the induction stroke. In other words, only half crankshaft rotation is available for the injection process at 6,000 RPM. This corresponds to an injection duration of 5 milliseconds. With gasoline direct injection, the fuel requirement at idle in relation to that at full load is far lower than the manifold induction factor 1:12 at idle. This results in an induction duration of approximately 0.4 milliseconds. Actuation of the STEV high pressure fuel injector. The high pressure fuel injector must be actuated with a highly complex current curve in order to comply with the requirements for the defined reproducible fuel injection process. The microcontroller in the engine ECU only delivers a digital triggering signal. An output module ASIC uses this signal to generate the triggering signal for the fuel injector. A DC to DC converter in the engine ECU generates a booster voltage of 65 volts. This voltage is required in order to bring the current up to a high value as quickly as possible in the booster phase. This is necessary in order to accelerate the injector needle as quickly as possible. In the pickup phase, TPK, the valve needle then achieves the maximum opening lift. See, when the fuel injector is open, a small control current, holding current is sufficient to keep the fuel injector open. With a constant valve needle displacement, the injected fuel quantity is proportional to the induction duration D. A comparison between gasoline and direct injection and manifold injection. WOT idle, injected fuel quantity, duration of injection in millisecond, manifold injection, gasoline direct injection. Actuation of STEV high pressure fuel injector, injected fuel quantity as a function of injection duration. A shows a triggering signal, B shows the current curve in injector, C needle left, and D injected fuel quantity. Inductive ignition system, ignition of the air fuel mixture in the gasoline engine is electric. It is produced by generating a flash over between the electrodes on a spark plug. The ignition coil energy converted in the spark plug ignites compressed air fuel mixture immediately adjacent to the spark plug, creating a flame vent which then spreads to ignite the air fuel mixture in the entire combustion chamber. The inductive ignition system generates in each power stroke the high voltage required for flashover and the spark duration required for ignition. The electric energy drawn from the vehicle electric system is temporarily stored in the ignition coil. The same figure shows the principle of layout of the ignition circuit of an inductive ignition system. It comprises the following component: ignition driver stage, which is integrated in the motronics ECU or in the ignition coils, spark plugs, and connecting devices and interference suppressor. Generating the ignition spark, a magnetic field is built up in the ignition coil. When a current flows in the primary circuit, the ignition energy required for ignition is stored in the magnetic field. The current in the primary winding only gradually attains its set point value because of the induced current voltage, counter voltage. Because the energy stored in the ignition coil is dependent upon the current E is 1 by 2Li2. A certain amount of time, 12 period, is required in order to store the energy necessary for ignition. This 12 period is dependent on, among others, the vehicle's system voltage. The ECU program calculates from the 12 period and the amount and the moment of ignition cut-in point and cuts the ignition coil in via the ignition driver stage and out again at the moment of ignition. Interpreting the coil current at the moment of ignition causes the magnetic field to collapse. This rapid magnetic field change induces a high voltage on the secondary side of the ignition coil as a result of the large number of turns ratio approximately 1:100. When the ignition voltage is reached, flashover occurs at the spark plug and the compressed air fuel mixture is ignited. Ignition circuit of an inductive ignition system terms 4 time 1 time 48, 1 volt, 12 volt battery is connected. Voltage curve at the electrodes. 1 is the battery, 2 AAS diode integrated in ignition coil, 3 ignition coil with iron core, and primary and secondary windings, 4 ignition driver stage integrated either in motronics ECU or in ignition coils, 5 spark plug, term 1 to term 4, 48, 15 terminal designations. In figure 10, K is the spark head, S is the spark tail, and DF is the spark duration. Flame front propagation. After the flashover, the voltage at the spark plug drops to the spark voltage. The spark voltage is dependent on the length of the spark plasma, electrode cap, and the friction due to flow, and the ranges between a few hundred volts and well over 1 kV. The ignition coil energy is converted in the ignition spark during the combustion time. This ignition spark duration lasts from as little as 100 microseconds to 2 milliseconds. Following the breakaway of the spark, the damped voltage decays. The electrical spark within the spark plug electrodes generates high temperature plasma. When the air fuel mixture at the spark plug is ignitable and sufficient energy input is supplied by the ignition system, the arc that is created develops into a self-propagating flame front. Moment of ignition. The instant at which the ignition spark ignites the air fuel mixture within the combustion chamber must be selected with extreme precision. This variable has a decisive influence on the engine operation and determines the output torque, exhaust current emission, and fuel consumption. Influencing variables that determine the moment of ignition are engine speed and engine load or torque. Additional variables such as, for example, engine temperature are also used to determine the optimal moment of ignition. These variables are recorded by sensors and they relate to the engine ECU of motronics. The moment of ignition is calculated and the triggering signal for the ignition driver stage is generated from program maps and characteristic curves. Combustion knocks occur if the moment of ignition is too advanced. Permanent knocking may result in engine damage. For this reason, knock sensors are used to monitor combustion noise. After a combustion knock, the moment of ignition is delayed too late and then slowly moved back to the pilot control valve. This helps to counteract permanent knocking. Schematic representation of the ignition coils ABC, terminal 1, terminal 4, terminal 1, terminal 4, terminal 1, terminal 4. Voltage distribution takes place on the primary side of the ignition coil, which are directly connected to the spark plug. Static voltage distribution system with single spark ignition coils. Each cylinder is allocated an ignition driver stage and an ignition coil. The engine ECU actuates the ignition driver stage in specified firing order. However, the system does also have to be synchronized with the camshaft by means of a camshaft sensor. System with dual spark ignition coils. One ignition driver stage and one ignition coil are allocated to every two cylinders. The end of the secondary winding are each connected to a spark plug in different cylinders. The cylinders have been chosen so that when the one cylinder is in compression cycle, the other is in exhaust cycle, only possible with engines with an even number of cylinders. It does not therefore need to be synchronized with the camshaft. Flashover occurs at both spark plugs and at the moment of ignition. Ignition coil, compact ignition coil design. The compact coil's magnetic circuit consists of O core and the I core, onto which the primary and secondary windings are plugged. This arrangement is installed in the coil housing. The primary windings, I core wound in wire, is electrically and mechanically connected to the primary plug connection. Also connected is the start of secondary winding coil body wound in wire. The connection on the spark plug side of the secondary winding is also located in the housing, and electrical contacting is established when the windings are fitted. Compact coil design, one pointer circuit board, two ignition diversity, 3 AS diode, activation or suppression, 4 secondary winding body, 5 secondary wire, 6 contact plate, 7 high voltage pin, 8 primary plug, 9 primary wire, 10 I core, 11 permanent magnet, 12 O core, 13 spring and silicone jacket is 14. Integrated within the housing is the high voltage contact room. This contains the contact section for spark plug contacting and also a silicone jacket for insulating the high voltage from the external components on the spark plug well. Following component assembly resin is vacuum injected into the inside of housing where it is allowed to harden. This produces high mechanical strength, good protection from environmental influences, and outstanding insulation of high voltage. The silicone jacket is then pushed on to the high voltage contact room for permanent attachment. Remote and COP versions, the ignition coils compact dimensions make it possible to implement the design shown in figure 12. This version is called COP coil on plug. The ignition coil is mounted directly on the spark plug, thereby rendering additional high voltage connecting cables superfluous. This reduces capacitive load on the ignition coil secondary circuit. The reduction in the number of components also increases operational reliability, no rodent bites in ignition cables, etc. In the less common remote version, the compact coils are mounted within the engine compartment using screws. Attachment lugs or an additional bracket are provided for this purpose. The high voltage connection is effected by means of a high voltage ignition cable from the ignition coil to the spark plug. The COP and the remote versions are virtually identical in design. However, the remote version mounted on the vehicle body is subject to fewer demands with regard to temperature and vibration condition due to the fact that it is exposed to fewer loads and strains. Pencil coil. The pencil coil makes the optimal use of the space available within the engine compartment. Its cylindrical shape makes it possible to use the spark plug as well as a supplementary installation area for ideal space utilization on the cylinder head. Because pencil coils are always mounted directly onto the spark plug, no additional high voltage connecting cables are required. Here is a design of a pencil coil, one plug connection, 2 printed circuit board with ignition driver stage, 3 permanent magnet, 4 attachment arm, 5 laminated electrical sheet, steel core, rod core. Secondary winding is 6, primary winding is 7, 8 is housing, 9 yoke plate, 10 permanent magnet, 11 high voltage dome, 12 silicone jacket, 13 attached spark plug. Design and magnetic circuit pencil. Coils operate like compact coils in accordance with the inductive principle. However, the rotational symmetry results in a design structure that differs considerably from that of compact coils. Although the magnetic circuit consists of the same material, the central rod core, figure 13.5, consists of lamination in various bits stacked in packs that are virtually circular. The yoke plate that provides the magnetic circuit is a rolled and slotted sleeve, also in electrical sheet steel, sometimes in multiple layers. Another difference relative to the compact coils is the primary winding, which has a longer diameter and is above the secondary winding, while the body of the winding also supports the rod core. This arrangement brings significant benefits in the area of design and operation, owing to restrictions imposed by the geometrical configuration and compact dimension. Pencil coils allow only limited scope for varying magnetic circuits, rod core, and yoke plate and windings. In most pencil coil applications, the limited space available dictates that permanent magnets be used to increase the spark energy. The arrangements for electrical conductor, spark plug, and for connection to the engine wiring harness are comparable with those used for compact pencil coils. Thank you.